Okay, so then you can just say, if you set it everything right, this is the program script. And then you can type like this, then you can make it in the background, or you can just foreground. Let's make it background run, and then it's running. Okay, so let me go to check. Oh, so basically, if you type S1 OPT log, so this is doing the calculation, as you can see that. And let me explain it a little bit about the structure of log file. Okay, so this is the first part, and this is the input geometry, as you can see, and other keywords here. And then there is it is a bit too big, so let me reduce it a little bit. Oops, sorry. So then you do the SCF calculation here, right? So you've probably seen this. This is the process when you optimize your molecular orbitals to get the orbitals. So once this is done, it says that SCF convergence achieved. Okay, and then it calculates something. But as I told you, this is the ROHF. Let me check whether, yeah, final ROHF energy, right? So because this is a T1 calculation. Now, once the orbital is obtained, and it prints out the alpha orbitals and beta orbitals. So this will be a huge. So let me quickly go. But let me go to search MRSF part. So it prints out everything. Then it does MRSF energy calculations here. So basically, you don't need to know this. It says that the Davis algorithm for singlet response states, which meaning that it will calculate singlet states. And then this is the iterative process. Then it will print out here state number 1, right? And then energy and respect to reference T1 states. Okay, so this is not absolute energy. This is a relative energy with respect to your reference T1 states. And these are the coefficients and important, let's say this one, important coefficients. Using this, you can figure out what kind of transition it is composed of, right? So because we ask 5 states, it prints out 5 states. Let me reduce the little. So then here, these are the final outcome of summarized. Here, 0 is a T1. Okay, it says that the RHF, or depending on situation, it can be UHF. So this is T1 energy. This is the reference. And from there, state number 1 is negative, meaning that the S0 is lower than T1, usually the case. So this doesn't mean it's a negative energy, right? With respect to T1, it's a negative. So now, so S0 is, from the S0, you can say T1 is higher than S0, right? So, but with respect to reference, it can be negative. So don't worry about this as a negative. So you can use this as your new reference as a 0 value. So because of this, we set it to 0. This has to be number 1, which becomes S0. And state number 2 is S1. State number 3 is S2, and so on. So, and if you have any doubts and questions, please. So it's confusing, but it's logical. But maybe we need to change it later. But it's not. We better not to, because I think this is there's a reason behind this. So 0 is for the reference. All the other states from number 1 is a response state. So number 1 is S0. Okay, so okay, so now, okay, this is also very nice because now what about from the S0, if you make S0, then T1 is 3.496, right? So you can use this column rather than this column. S square is the S square, the spin square value, average value, expectation value. If it's 0, it's a singlet. Okay, so if it's 2, it's triplet. So this means that these are singlet. It's telling me that these are singlet. Now these are the transition dipole moments, x, y, z, and absolute value is here, which directly related with oscillator strengths here, like this. Meaning that with respect to S0 here, right? So S0 by itself is 0, right? So it's a 0. But from S1, sorry, from ground state to S2 has a large value, something like this. And this is how you interpret this. Right now, it does not print out. You can also think about the oscillator strength from S1, right? It looks like this is dark state from the ground states, but you can also think about from S1 to other higher states, which we can also calculate, but we're not printing out here. Okay, so once you compute these energies, then here, please carefully look at this. Entering gradient calculation, gradient of what states? Root 2. Root 2 is S1 state, which is this state. So this 2 corresponds to this 2. So we need to be very, very careful. I mean, because we ask 2, it will optimize root 2, which is S1 states. So then based on these value, it computes gradients, right, of root 2. So basically, these are the gradient. Using this gradient, it tries to find out the next geometry optimization step 2, and these are the refined geometry, right? So this is how this is all. And if you run the geometry optimizations, you will see interesting files here: OPT geom XYZ, OPT status, OPT XYZ. So OPT status, if you look at the OPT status, it will basically prints out the status of optimizations. Oops. So it's done. Oh, it's done. Okay. So status, if you look at status, it grabs the energy of each geometry. So here up to 30 geometry, and this is energy shifts, and you can understand what it means, and then gradients. So the gradient at the end of geometry optimization, gradient has to be very small. So using those, it will figure out. Okay, and then there is another file, OPT geom, is we print out all the geometry changes along the so up to the 30, so you can see all the geometry changes. And then there is OPT XYZ, which only give you the last geometry. So that means that you can use it for another calculation. So let us, but don't assume that your program did it properly and correctly. So let's check the log file again. And this is the last part of a log file. It says that geometry optimization has not converged. So don't expect that once program stopped that everything is properly done. No, that would never happen. So geometry optimization has not converged, reached the maximum iteration, meaning that the default iteration is a 30, so it reached the 30, so it's just a stop. But the geometry is not optimized. So what you can do next is that you create another file like OPT. I actually created this second trial for the optimizations. And you can either say OPT here. I think that is something I recommend because OPT has a lost geometry. Or you just let it time in here. But here all the other the same. But here, initial guess, I said that, well, why don't we read the one that is saved before? Okay, so